Welcome. My name is Dan Stieler. I work for PowerFilm Incorporated. Today we're going to talk a little bit about powering your IoT devices by energy harvesting of solar energy in low light and indoor and low light environments. The basic breakdown of an IoT powered system is four main components. The first component is a energy harvesting IC, which is the integrated circuit that actually does the energy harvesting. It may also have a communication module like a Bluetooth or Wi-Fi or some other sort to be able to relay information back to the place that's doing the data collection, and then also a data processing integrated circuit to go along with that to do the data processing up from a sensor. It's going to have some energy storage, whether it be battery or supercapacitor, anything of that type. There will be a sensor, which is what's collecting the information for the system. And then finally, we're going to focus on IoT powered by solar panels, so that you'd also have some sort of solar panel that would be feeding in and powering the system. First, we're going to talk a little bit about the energy storage technology considerations. A few things to think about when you're designing your system are the application voltage, the voltage that your system's going to need to operate at, whether it be something around the 1.8 volt range or 3 volt range, or maybe even higher, maybe up to, if it's a lead acid battery, maybe up in the 12 volt range, depending on how much power your system takes and what you're doing. Most of this talk is going to focus on lower power systems, so lower voltage batteries or storage elements will be what we'll primarily focus on. Other considerations when you're choosing a storage element are going to be something like self-discharge rate, self-discharge temperature dependence. So if your battery, depending on the technology, it may lose 1% or 2% a day. It may only lose 0.5% a month or less. It varies quite a bit. Supercapacitors, for example, you might lose almost 50% of the stored charge per day. And those have a temperature dependence, so if you go to higher temperatures, they're going to discharge more quickly, so it's very important to understand what your application is and what the temperatures that you will see will be. There's also charge efficiency. Each of the different types of storage elements have a slightly different charge efficiency. Charge efficiency is defined as the amount of power that you put into the storage element versus the amount of power you actually get out of the storage element. So, ideally you'd want something close to 100%, so you're not wasting a lot of power when you're charging. And we'll see in a little bit that the different storage elements, there's some slight variations in charge efficiency for them. And the other consideration is the depth of discharge and cycle life. Depending on the battery technology and chemistry, you'll get different cycle lives. You may get a cycle life that's in the 1,000, 10,000 range. You may only have a cycle life in a few hundred charge cycle range. And a lot of that is dependent on the depth of discharge. If you look at the plot over in the bottom right-hand corner, you'll see that, for example, with lithium iron phosphate batteries, if you're only discharging 5% of the battery capacity, you may get 15,000 cycles. But if you're discharging down to 75% of the full capacity, now you're down in the range of only 1,000 cycles. So the actual depth of discharge makes a big difference on the life of the battery. Battery capacity, it varies with the rate that you're discharging. So if, for example, your sensor takes 15 milliamps of current to operate, or their whole system, the whole IoT system takes 15 milliamps of current average to operate, you're going to have one capacity for the battery. If it takes 30 milliamps, the batteries actually will have a slightly different lower capacity. So if you look at the chart on the right-hand side here, you'll see that there's a few different battery manufacturers listed, and they each have a slightly different battery capacity for the same type of battery. These batteries were all the same model battery, the same claimed capacity. And you can see that depending on the discharge rate and depending on the manufacturer, you're getting quite different total capacities. The one thing to note about the capacity that's quoted, usually the capacities that the manufacturers tell you are the capacities for low rate steady discharge current. So, It may be a 10 milliamp current draw is what they do their capacity rating at. In the case of this particular battery, which is a CR2032, it's probably somewhere in the 10 to 15 milliamp range that they figure the capacity is typically on. I would like you to note that the non-name brand batteries over in this on the right-hand side of the plot did not have any particular capacity listed. They just were listed as 2032s, and you can see that they are much lower. Capacity, like I was just saying a little bit ago, it varies with discharge rate. Here's a plot that shows you what your battery capacity would be at various discharge rates, and this is for a ML1220 cell. If you're doing a very low rate discharge, you're going to get almost 16 milliamp hours out of the battery. As the rate increases up to 10 to 20 milliamps, you're getting very, very few, less than 1 milliamp hour out of the battery. And this is where it becomes important to pick the specific storage technology. Some storage technologies are better at discharging at high rates than others, and you're going to get better capacity or better performance out of them. These plots here on the left-hand side show what the battery discharge profiles would be for a number of popular battery types. Lithium ions on top, lead acid, nickel zinc, nickel cadmium, nickel metal hydride, and zinc manganese oxide batteries. On the right-hand side, there's a discharge profile for a supercap. You can see, for example, some of the technologies have very flat discharge profiles. Take, for example, the nickel cadmium or nickel metal hydrides. You start off at maybe 1.35 volts, and when it finishes, it's finishing at 1.2 volts, so it's a pretty tight area. If you look at the lithium ions will start up at about 4.2 volts and end at about 3 volts, so you got a lot of variation over the course of the full discharge in order to access all the capacity. So this kind of thing, choosing the discharge profile is another thing you want to consider when choosing your application. Depending on what your application is and what the discharge profile of the battery is, you may or may not need some sort of voltage regulator to feed into the other electronics that you're going to be powering. And that just depends on what the tolerances are on the electronics you're using. The supercapacitor plot on the right-hand side shows once again the voltage versus time for the discharge profile, and you'll see that the discharge profile for the supercap it's not quite linear, but it's nearly linear, so you're losing, or your voltage is decreasing a lot between full capacity and end capacity. And so when you're dealing with a supercap, what you need to do is you need to look at what your fully charged voltage is and what your minimum voltage is, and actually go back and calculate how much charge you can store in that voltage range, not the amount of charge that the supercap can store totally, because you're only ever going to be able to access the amount of charge that's between the max voltage on the supercap and the minimum voltage for your electronics. Here's a table showing a number of the different storage technologies and comparing them to each other. You can see what the cell voltages are for a number of different technologies, the self-discharge rates, energy densities, charge efficiencies, the typical cycle durabilities, and then just kind of a comment on yes or no whether or not the discharge curve is fairly flat. So you can see, like with the nickel metal hydride and nickel cadmium, I'm commenting they have a fairly flat discharge like you saw on the previous slide. What you'll see here with the cell voltages is you see that a lot of the technologies, nickel cadmium, nickel metal hydride, the alkalines, they're all less than a 1.5 volt or less, which means in many cases you're going to need some kind of boost circuit to boost them up to power the electronics you'll be powering, or you're going to need to use 2 series connected cells. Something like the lithium ion or the lithium iron phosphates or the lead acids, you're going to be able to power a lot of the modern day electronics for IoT sensors from just a single battery from a voltage perspective. Looking at the self-discharge rates, you see that the low discharge nickel metal hydrides and the alkalines are some of the best ones you can get, very low percentage loss per day. The lithium-ion batteries have a moderate loss per day, and supercapacitors get to be a pretty high loss per day. In addition to the old nickel metal hydrides before the low discharge ones came out, they were extremely high percentage of loss per day. You'll also notice that the charge efficiency is listed there, and the charge efficiencies for the nickel metal hydrides is pretty low. It's only about 66%. You move into something like a lithium ion or lithium iron phosphate, and you're up in the 80 to 90% range, which is much better. The one thing to consider when you're looking at charge efficiency and self-discharge rate and choosing a technology is you want something that's going to charge efficiently, but you also want something that's not going to self-discharge very quickly. And that goes into how you're going to size your solar or your energy harvesting equipment. Because if you're in a low light environment and you're only energy harvesting a very small amount of power, if you choose a battery that's much larger than you need, since the self-discharge rates are based on a percentage, you're going to find that you have issues with self-discharge being higher than the actual charge rate. So oversizing a battery doesn't necessarily mean you're going to get a better or longer lasting system. You need to have the battery sized right for both your electronics and then for the energy harvesting equipment that goes into it. To get the most from your battery storage, you need to take a look at the different battery vendors and battery options. Vet the battery vendors, test their capacities, and make sure that you have a capacity or battery that meets the capacity requirements that you have. And that has to do with both the amount of current that your application will use and the actual battery manufacturer. You can actually increase the capacity of your battery in many cases if you're doing things with pulse that require high pulse currents, like wireless communication. The Bluetooth, Wi-Fi, cellular, they all rely on transmitting and receiving with very high burst currents. And so those burst currents will pull the batteries down very quickly. But if you put a capacitor in parallel with them on the input side, you can actually access a lot more of the battery capacity even at those really high pulse currents. So the plot on the right-hand side here shows what the percent capacity was and what the capacity loss was going from a higher current to a lower current. And that helps give you an idea of, if you can reduce your average current draw from your battery by putting a capacitor in place, you're going to be actually moving to a lower average current, which is going to give you a higher capacity coming from your battery. And it also gives you a lower depth of discharge because you're not pulling those really high currents from the battery and pulling the battery down. So consider adding a capacitor on the input side along with a battery device just to keep the storage increase the storage lifetime, I guess. In order to have a long-lasting system, you need to add some generation capability. And so there's two parts to adding the energy generation. The first part is an energy harvesting IC, which is an integrated circuit. And so an energy harvesting integrated circuit that's optimized for solar is going to have one of three different ways to access the solar energy. So a solar IV curve looks like what you see down here on the bottom of the screen. This particular plot shows a family of IV curves, one at 200 lux, which is the red line, one at 400 lux, which is the blue line, and one at 1,000 lux, which is the purple line. So you can see that the amount of power that you're getting out of your solar cell is dependent on the intensity of the light that you have coming into the solar cell. Now the energy harvesting ICs can do one of three things. On the IV curve, you want to optimize the amount of power that you're able to get from the solar cell, and that depends on where you're at on this particular IV curve, and that really depends on the input impedance of the energy harvesting circuit. So there's like I said, there's three ways to go about it. The first is using a fixed set point. Some of the energy harvester ICs will take and set a fixed point. So, for example, here I've got a line drawn on the plot. This yellow line, excuse me, this yellow line shows about what the set point would be if it was set at a little over 2.5 volts. And you can see that in one case, or in all cases, it's not right on the maximum power point. So the maximum power point of these individual IV curves is denoted by a black triangle. And so on average, you're getting, in one case, you're getting something that's a little higher than the maximum power point. In another case, you're getting something that's a little lower than the maximum power point. But it's just in a fixed spot all the time. And so that's okay, depending on your application. But if you're looking at really wide swings in intensity of the solar cells, that probably means that you're not going to be collecting as much current in any case as you potentially could. So there's a second way to do it. The second way is ratio power point tracking. And what ratio power point tracking is it's looking at and taking the open circuit voltage of the cell, which is going to be the voltage down here in the bottom right, so whatever the voltage is when there's no current flowing, and then multiplying by that by some factor, so 0.7 for 70% or 0.8 for 80%, and looking at what it's setting the power point then, or the point at which it's going to collect power at 70 or 80 or 90% of what the open circuit voltage is. So if we look at what a ratio power point tracking system would do on these IV curves, you can see the green diamonds show where you're at for ratio power point tracking. And it's significantly better than just doing a fixed set point track. You can see that it's not right on the maximum power point, but it's not bad. And then finally, maximum power point tracking would be the optimal way to collect the power, and that's, like we talked about before, is where the black diamonds are. So those are at the absolute maximum amount of power that you can collect from a cell. Some of the energy harvesting ICs have some neat features. A lot of them have integrated battery charging, so you can set it up to charge to whatever float voltage your specific battery or storage technology takes. They'll have under and over voltage protection to protect the battery, so it's not, if you over voltage your battery, you're going to reduce its life. If you under voltage your battery, you're going to reduce its life, so the electronics will keep your battery in that particular window and optimize the battery life for you. They're good at very low voltage power collection, which comes into play when you're using few numbers of individual solar cells in really low light conditions, and we'll get into why that is in a little bit. And then other things like being able to add a primary battery to the system, so you'd have both the secondary battery or rechargeable battery and a primary non-rechargeable battery as backup for times when, say, something happens and you don't have enough light to make it through a long, if a plant's shut down for a week or a long period of time, and it's not in your initial use case scenario, the primary battery would then kick in and pull through until you were able to start charging again, have the lights returned back on in the facility or whatever your application may be. They can provide regulated outputs, so if your electronics run at 2 volts, they could provide a 2 volt regulated output coming off the battery to power them. They're focused on efficiency, so they tend to be very high efficiency in general. And the price, there's a wide range of different prices we'll see in a little bit. The picture down in the lower right-hand corner of this slide shows a energy harvesting development kit that PowerFilm actually sells. And this particular kit has a TI chip that is capable of doing the energy harvesting and then also provides a regulated output. Here's a table showing a few of the solar optimized energy harvesting integrated circuits. So you'll see that you've got the first three, they have ratio power point tracking. They're able to turn on at very low voltages. Cold starts at 0.33 volts. And once they start up, you can go to a much lower voltage, down to about 1/10 of a volt. They offer under and over voltage lockouts. status outputs to tell you what the status of the battery is, and they're very efficient, 92 to 95%. Moving down to about the fourth one. The fourth one is an interesting one because it's a chip by Linear Technology. Now, it only offers set point tracking, or just a set point ability to access power on the IV curve, but it does do both boosting and buck conversion. So if you were, and it also allows you to go to it allows you to go to higher voltage. So if you had a panel and it was at a really low voltage in the low light environment, but you were maybe the system is indoors and outdoors, or it changes from location to location, so sometimes it may be at a much higher voltage, you may choose something like this linear chip to be able to get optimal power generation in all environments. Then there's a few other chips. The one interesting thing to note is the SPV 1040, which is the second one from the bottom, is the only chip on the list that does true maximum power point tracking. So that's something that you may be interested in. It's also a little higher power chip, and not too expensive. So it doesn't have all the features of the other ones, like a lot of the TI chips. One of them has the primary battery function that was talked about earlier. The SPV 1040 is kind of a bare bones thing, but it does maximum power point tracking. It does relatively high powers. So depending on your application, that may be the right one for you as well. Okay, now we're going to get into a little bit about the different solar technology considerations and how solar works. Some things you may want to take into consideration when you're designing a IoT system to work in a low light or indoor environment are how is the solar panel going to be mounted? Is flexibility important to you? If you look at the picture in the upper right hand corner, you can get cells that are very flexible. And that's what PowerFilm specializes in. There's other cells as well on the market, which I'm sure you've all seen, that are on glass panels or just crystalline wafers. And they don't provide a lot of flexibility, but they are they're solar technologies as well. Durability, depending on your technology, you may need extra durability. Something like the PowerFilm technology that's on a plastic substrate provides a great deal of durability compared to glass or crystalline solar cells. Very impact resistant. You can actually poke holes in them, shoot holes in them, any of that kind of stuff, and the power still remains very similar to initial. They tend to, if you put a hole in it or something, it'll degrade by that amount of area loss, but not a whole lot more, where if you were to do that to a glass panel or something, you would probably pretty much lose all of the power. If weight's important to you, you want to make sure to evaluate your solar technologies based on weight. Like I said, the amorphous silicon technologies, especially the ones on plastic, are very lightweight compared to glass because the plastics are much thinner and much lighter to begin with. Ease of product integration. Do you need something like a back contact? Are you going to solder? Are you going to spot weld? Does the panel need to be conformable, which is kind of what we talked about with the flexibility part of it? And do you want a single or a multi-piece panel? With the amorphous silicon technology that PowerFilm produces, we customize to a given application's voltage and current levels, and we do it all in a single piece. It's got a printed and laser welded interconnect that makes that strings all the cells together and makes an extremely durable form factor. Other things to consider when you're designing is your anticipated light source and light level. Depending on the solar technology chosen, they will perform differently under different light sources and at different light levels. Voltage requirements. The voltage requirements go back to what the technology you want to use is. Say, for example, a crystalline silicon technology, for every cell you only get a half volt out, and you're going to have to string them together manually. For like the amorphous silicon technology, like I said, we make individual pieces that are all pre-strung together and in one little coupon, and you can get almost any voltage you want out of those coupons. Amorphous silicon itself, a single junction amorphous silicon is about, at power point, about 0.6 of a volt per cell, and a tandem junction one would be about 1.2 volts per cell. Then you also have to consider environmental factors for the solar. Are you in a very wet environment, high humidity, high temperature, exposed to a lot of UV? Is the panel going to be seeing temperature cycling? All these things have to play into what type of encapsulation you may want to use in the solar cell to make sure that it gets the longevity that your application requires. On this slide, we're going to look at some IV curves for the solar cells and just discuss about how the solar works. Here's a family of IV curves going from 200 lux all the way up to 1,000 lux. Like we saw before, the current changes proportionally with light intensity. The voltage only slightly decreases at higher light intensities. So if you're looking at using it outside, 100% sun down to almost about 10% sun, the voltage really stays about the same. When you start to get under 10% sun, then other factors start to kick in. Leakage paths become more dominant within the cell that cause shunting of current, and the shunting of current reduces the voltage. So this is something that every technology has to deal with. Some are better at it than others, and we're going to see some plots for the amorphous silicon, how it performs, how the voltage changes as you change the light intensity and the light source. So this is the question I just posed: how will a solar cell respond in low light conditions? As you can see, up at 100%, coming down to close to 10%. I guess by the time you're down to 10%, you're probably down to about 90% of the initial voltage at 100%. But then it drops off fairly quickly as you get down into the low light area. So your low light intensity here is going to be in the 50 percentile of what the voltage was at the high intensities. And this is pretty similar to what you're going to see for most solar technologies. You can also tell that the power is kind of reducing at more of a linear rate. So the total maximum power, WPP stands for watts of peak power, decreases with light intensity fairly linearly. That previous one was for a non-low light optimized cell. Now if we look at a low light optimized cell, you see that the voltage stays much, much higher. In this case, for the low light cell, once you get down to even as low as 0.2%, or that would be the same as 200 lux, your voltage is still at about 80% of what it was at 100% sun. And your output power, your watts peak power, is still decreasing at a fairly linear rate. And so it's important if you have a low light application to have a low light optimized cell. One thing that people always wonder is why don't high efficiency technologies always perform better even in indoor environments? Well, the real reason is because efficiency in a solar cell is based on the full outdoor light spectrum and not on just like, for example, indoor light. Indoor light is very different than outdoor light. So if you look at the plot on the bottom of the screen here, you can see that this area over on the left-hand side where the colors are, those are the colors that you see, and the colors that are present in indoor lighting to some extent. And there's this whole other area out here in the infrared, the gray area, that is all light coming from the sun, and all that is used when calculating the efficiency of a solar cell. If you're not absorbing this light, then you're not going to be as efficient. But when you move to indoor lighting doesn't have that infrared as much, so your efficiency is going to go down. Excuse me. Or not necessarily go down, it's just going to change. I mean, the efficiency of collecting indoor light is very different than the efficiency of collecting outdoor light. Indoor light sources have a much more narrow spectrum, as we'll see in a couple seconds. And if you're using really high efficiency technologies like triple junction gallium arsenide, those technologies are set up to absorb over a wide range of light in order to be able to achieve their high efficiencies. And when you put them inside, the matching between the different junctions, or the amount of light collected by the different junctions, changes, and it decreases for the junctions that are supposed to be harvesting light out in the in the near infrared range, and basically throttles the cell back, so you're not getting very much power out of the cell at all comparatively. What is quantum efficiency? The quantum efficiency of a solar cell is how efficiently it is able to gather light of any given wavelength. So here's a few different quantum efficiency curves. I also have the quantum efficiency of a lux meter plotted over the top of them. So if you look at the black dotted line, that's a lux meter. So if you're going to buy a lux meter, measure lux, and try to determine what you need for your application as far as how much power you have and how much light intensity you have available, you can tell how much light intensity you have available based on the number of the lux reading on the meter. However, that lux reading means different things for different cells. So it's only got a very, very narrow quantum efficiency compared to a solar cell. So if you're collecting 400 lux with your lux meter, and you have, for example, this blue line here with the amorphous silicon cell, the amorphous silicon cell is collecting all this light over here outside of the lux meter range, so it actually has a lot more light available than just 400 lux of light. 400 lux is just a measurement to kind of give you an idea what the ballpark or what your application may be, and then you're going to have to go back and look at how your cells actually perform in those given light conditions. And PowerFilm specializes in matching applications like that. If you look over here in the bottom right-hand corner, this is one of the triple junction gallium arsenide cells I was talking about, and you can see that you've got one junction that's absorbing mostly in the 3 to 700 nanometer range. Well, if you look at here, 3 to 700 nanometers, you're somewhere right in here. And then you have other junctions that start to kick in. Well, in indoor lighting, as we'll see, once you get out to this 700-800 nanometer range, there's almost no light coming through. So you may have one whole junction that's really not able to gather much light at all, which is why these technologies do not do well on indoor lighting. Here's the spectral response of an incandescent and a halogen type light compared to a lux meter. And so you can see in this case the halogen and the incandescent, they're lower efficiency technologies. If you go and buy a halogen light and you want to put it in your office, you're going to use like a 75 watt light bulb, where a comparable LED light for something that has similar amount of light may only be 10 watts. So the reason for that is you have all this light out here in the over 700, 650 to 700 range that you can't see. Your eye can't see that light, and it's just basically used as lost to the room as heat. So that's why you maybe have a bulb that's 75 watts versus a bulb that's 10 watts, and your perception is that you have the same amount of light coming out. And one other note is that lux is actually kind of a measure of how your eye perceives light. So the lux meter is going to look very similar to what the efficiency of perceiving light of your eye is. So here's a comparison of some different technologies and how they perform in standard incandescent lights. You'll see that in the incandescent light, the technologies that really do well are the crystalline silicon technologies. And that would be these top two plots. As we go through these different plots, you can see I've got some part numbers here. These are standard part numbers you could find on DigiKey or Mauser or whatever. Commercially available cells to give a side-by-side comparison of. And then you'll notice that something like the triple junction gallium arsenide kind of comes in somewhere in the middle, and then the amorphous silicon cells are not collecting as much light because they don't collect out into the infrared as much as a crystalline cell or a triple junction gallium arsenide cell would. Now when we move to more efficient lighting, you'll see that something like the fluorescent lighting, here's a picture of a plot of the fluorescent light spectrum, and you can see that you don't have any of this light over in this area above 650 nanometers where that's basically just being lost as heat. That's why it takes less power to get about the same amount of light out, because the light that is coming out of the light is coming out in an area that you perceive it as a person. So it's a more efficient light source for us for lighting. And then as it turns out, the amorphous silicon cells in this case are on top. You'll see that the PowerFilm single junction amorphous silicon cell is on top of the pack up here, and then the tandem one follows, and then the couple other manufacturers of amorphous silicon are after that. The crystalline silicon cell, there's one crystalline silicon cell that's kind of in the mid-range, and then moving down there's the other technologies, other crystalline cells. There's your triple junction gallium arsenide, and then there's CIGS, which is kind of down at the bottom. That the CIGS cells in general don't do very well in the really low light conditions. And here is a plot of LED lighting compared to a lux meter, and you'll see that you once again you don't have a lot of light over in this area above 700 nanometers. You do have some light over here in the more blue area, but in general the light's really focused on in an area that's well perceived by your eye, which is why you put a lot less power into LED lighting when you're lighting up a room for people to work in. And as it turns out, the LED lighting is a good match for the amorphous silicon once again. Both the PowerFilm amorphous silicon cells are head and shoulders above all the other cells for like a 300K warm white LED light. Then you've got some other amorphous silicon cells coming in. You get down here and you've got your triple junction gallium arsenide and some crystalline silicon. And then once again, you know, the SIG cells, like I said before, don't do great in low light, and they're kind of at the bottom of the pack. For the 5000K color temperature cool white LEDs, you see basically the same thing going on. So finally, I want to just give an application example here. So what could we do, what could we power with solar and energy harvesting circuit? Well, you could potentially power your Kindle Touch. I looked into a 7th generation Kindle Touch. You know, battery life that's quoted by the manufacturer is about 14 weeks. That includes 14 hours of reading time and 658 hours of standby time. Which means that based on the battery in that device, it's using about 4.84 milliwatt hours of power. The size of the e-reader itself is 169 by 119 millimeters. And so let's see what we can find if there's some solar that fits that bill that you could use to produce that 4.84 milliwatt hours of power and fits on the back of would fit on the back side of the Kindle, so you could theoretically flip it over and let it sit somewhere and charge. One thing to note in doing something like this, you're typically going to want to bypass the internal charge electronics and connect directly to the battery, because the efficiency of the USB charging electronics oftentimes, especially if they're designed to be charged from a wall, is not going to be great. It's maybe going to be 70–80% efficient versus our energy harvesting chip, which is more up in the 90 percentile range. So what do? We're going to pick out an energy harvesting IC. I'm going to pick the TI BQ25504. Based on the plot on the right-hand side, I'm going to assume that our efficiency in general is going to be 85% or better. We want to make sure that when we're putting the circuit together, we use a low leakage flux in our solder so that you're not losing power through the flux, and you're not causing issues with the signals on the energy harvesting chip itself. If you have a flux that has a moderate leakage, you can actually change the signal on the different input and output pins on the energy harvester chip and cause it to do things that you don't necessarily want it to do. Also, we probably want to consider conformal coating it just to protect it from any environmental factors, moisture, humidity, those types of things. So we've got our energy harvesting chip, we've got our device, our battery. Next thing we need to do is choose the solar material. So we want to choose a solar material with a goal of 4.84 milliwatt hours of power. We're going to say we want the amorphous silicon because it's very thin, it's going to be very easy to apply to the e-reader. Not going to add much weight. If you set your e-reader down on top of it, or if you drop it on the floor or whatever, you're not going to damage the cells or break them. To fit on the back, we can choose a standard PowerFilm panel, 150 millimeter by 114 millimeter. The weight of the panel is going to be about 4.6 grams, so not very much. In the lower right-hand corner, you're going to see here's the power output of a panel that was specified there. So if you look down at about 1,000 lux, you can see that it's able to produce 4.67 milliwatts, which is close to your 4.84. So it's not a bad solution. If it was taken, and put in a window or someplace where you're getting a little over 1,000 lux, or taken outside just for a short amount of time, you could easily get over your 4.84 milliwatt hour goal. The other thing to note is that there's a lot of standby time built into that equation for the Kindle. If you're not letting it sit on standby, if you're actually turning your Kindle off, you're going to have no problem whatsoever powering it on solar, because you don't have that parasitic draw when you're not using it. And the same thing goes when you're designing an IoT sensor system. If you can use latency to transmit data in group packets and still maintain the amount of data integrity you want, the fewer times you transmit, the longer your battery life is going to be. If you want, say you're collecting temperature data and you want to collect temperature data every minute, but you really don't need you're not looking at that data, you're not using it for anything real time, so you really only need to transmit data, maybe every half hour or every hour. Then if you collect the data and transmit it in bursts like that, in packets, your energy usage goes way, way down, and that's going to enable you to use less battery storage, less solar, go longer periods of time, all those sorts of things. So really managing how you use your power is just as important as how you design the input power circuit to go with the device. Here's an example schematic of the circuit that I would use with the Kindle Touch for charging. You can see that in the upper area here, you've got the Kindle battery that you're tying directly into. This piece right here, all this is the energy harvesting layout. And then right here would be your amorphous silicon solar cell. So that would be an example of what you could do. I got a few references here. And I just want to thank you for your time today, and thanks for going through this presentation with me.